Welcome to this another video in the series on dynamics of system of particles. So this video is an extension of our discussion on angular momentum for a system of particles. Angular momentum for a system of particle we had already defined in a previous video. So for that we first defined angular momentum for a single particle like this formula. So there what we did was we took the moment arm, that is the vector joining reference point A to the particle of which we are interested in calculating the angular momentum. So we took this vector Ri minus Ra and took its cross product with the MIVI, that is the linear momentum of the particle. And when we add this up, these quantities HI's for all the particles in the system, we get angular momentum of the whole system. So we had seen this in some detail. Now what we are interested in dealing with in this video is relative angular momentum. So this is another quantity which is very similar to angular momentum, and it is sometimes easier to deal with than the angular momentum itself. So while solving problems, sometimes it is easier to use relative angular momentum rather than angular momentum itself. So relative angular momentum for a system of particles about a reference point A is denoted by HA prime. Now how do we define relative angular momentum? So for that purpose, we first define relative angular momentum for a single particle, the ith particle. So relative angular momentum Hi prime with respect to some reference point A is defined like this: Ri minus Ra cross Mi Vi. So this is basically our definition of angular momentum. To change this into relative angular momentum, we have to replace this Vi velocity by Vi slash A, that is velocity of the ith particle with respect to, so this is the relative velocity of ith particle with respect to point A, our reference point. So this is the only difference in the definitions of relative angular momentum and angular momentum. That is, in relative angular momentum we are going to use relative velocity of the particle with respect to the reference point A. Now to get a relation between rate of change of relative angular momentum and external moments applied to the system, we will take derivative of this equation. So Hi prime slash A, so this is a vector quantity, so its derivative will be, so if I take derivative of the first term, it will be Vi minus Va, which is nothing but velocity of I with respect to A. So this is basically velocity of I with respect to A cross M Vi slash A plus Ri minus RA cross Mi acceleration of ith particle with respect to the point A. Now this term and this term, they are same and they are in cross product, so basically this whole term is going to be 0. And what about this term? This term can be expanded into, so ai slash a can be expanded into ai minus aa. Therefore hi slash a prime is equal to ri minus ra cross mi ai minus ri minus ra cross mi aa. Now in order to obtain, so this is rate of change of angular momentum for the ith particle. In order to obtain ha dot, that is the rate of change of angular momentum of the whole system, we will sum this the equation above from I to up to n. So over I we will sum all these angular momenta, relative angular momenta rather. Okay, now this first term we have already seen is basically sum of all external moments, because in moment of internal forces cancels out, and this ai is basically miai from Newton's second law gives external and internal forces acting on the ith particle, and there is its moment, but the moments due to internal forces cancel out over summation. So this is basically angular momentum about A of all external forces. So therefore HA dot is equal to MA plus, so we will expand this term here, so it has negative sign. So when we will expand this, so we will write it like this: MI RI okay. So this is summation over I, MI RI minus summation, rather let me write RA first, and cross A. Now this quantity is basically from the definition of center mass, it is equal to m rcm, and this is total mass m. Therefore ha dot, so angular moment, rate of change of relative angular momentum, there is prime all over here, so rate of change of relative angular momentum is equal to about some point A is equal to net external moment about that point A minus m r c m minus r a cross a a. Now we can simplify this relation for some cases, actually 3 cases. So the simplified relation is the easier to remember relation, that rate of change of relative angular momentum is equal to net external moment acting on the system if, so there are few cases for this is valid. So one such case is when this term is 0, that is when RA is equal to RCM. If, so the cases are if RA is equal to RCM, that is our reference point is the center of mass itself. Then second case in which this this term will be 0 is when AA is 0, that is so there is or condition here, huh? So if any one of these condition is satisfied, then the relation on the left will be valid. So either A is center of mass or A is not accelerating or the third condition is when the direction of AA is such that it is parallel to RCM minus RA, that is A is accelerating towards or away from center of mass of the system. So these are basically 3 cases for which this simple relation between rate of change of relative angular momentum and external moments is valid. All right, now we will take a simple example to illustrate this relation. So the example is as follows. So suppose we have a support and from which there is a cord which is hanging, and from that cord there is a bar. a very light bar or rod is hanging from this light thread. Okay, now from this are suspended along this bar are two masses. So there is this big mass and a smaller mass. So initially this system is at rest. So this is support and this is cord and this is rod, a rigid rod, and this mass is 2m, this mass is m. Now there is a force which is applied. So the system initially was at rest, there is a force F which is applied. So if the distance between these two is given as d and the distance between this mass and the point of application of force is given as c. Now we are asked to find two things. First thing is acceleration of the center of mass. This is very easy. So acceleration of center of mass can be found by using the Newton's second law for a system of particles, which says that net external force acting on the system is equal to total mass of the system into acceleration of center of mass. Now we are interested in finding the acceleration in the x direction. Then we can write F is equal to total mass is m plus twice m into a. So this is acceleration of center of mass. So a cm is equal to F over 3m. So this is xcm. What about y acceleration at this instant? So for that you will have to take into account tension in the cord and the gravity force. So the gravity force and the tension, they cancel out. So the next net external force is 0. So there is no acceleration in the y direction. So this is the only acceleration which is in the x direction at this point. At the next point the situation will be different. Now the second thing which we are asked is rate of change of angular velocity of this rod, that is we are asked to find theta double dot for this rod. So to do that, what we will do is we will first locate the center of mass of this system. So this is very easy for this system. You can easily show that center of mass is at a distance of d by 3 from the larger mass. So this is center of mass is here. Okay. Now what we will do is we will calculate the relative angular momentum of the system. with respect to its center of mass. So to find relative angular momentum, we, for the first mass m, we have mass m and its relative velocity with respect to the center of mass. So this mass is at a distance of 2d by 3 from the center of mass, and its relative velocity with respect to the center of mass will be given by 2d over 3 theta dot, using the formula v is equal to r omega. So remember that this is relative velocity with respect to the center of mass. So if theta dot is in the counterclockwise direction, then this will be v theta is equal to r theta dot, and r here is 2d over 3. Similarly, we will have 2m for the larger mass, a moment arm of d by 3 and a velocity of d over 3 theta dot. If I take its derivative, I will have, and I sum this up, so this is 4 by 9 plus 6 by 9, so this is basically twice m d square by 3, and since I am taking time derivative, so this will be theta double dot. And now by relation between rate of change of relative angular momentum with respect to the center of mass, I can equate this with the moment of net moment of all external forces about the center of mass, which will be F into C plus d by 3. So basically this distance, and from this I can find my value of theta double dot. Okay, so thank you.